last session of this very exciting conference, this birthday celebration conference. Please take your seats and fasten your seat belts for the final talk. The final talk will be given by Eric Vanden-Eijden of Courant Institute at NYU in New York. And I will not read his title because you can see it and he will explain everything. Eric.
Is this on? Okay. So, like everyone else, I'm very, very happy to be here to celebrate the birthday of CECAM. Like pretty much everyone else, the CECAM was instrumental in my career too. At some point, maybe, well, actually 20 years ago, was the beginning of many developments in rare event calculation, and there were many meetings over there that were, quite keen to this development with Giovanni Cicotti, of course, but David Chandler was there, and all his, the people around him, Peter Bolhuis, Chris Delago, Phil Geisler. There was Ron Elber was there. It was really a very, very nice group of people going to these workshops, and they were really workshops in the sense that there were really a lot of things that came out of that. And that I really remember fondly. So I'm the last talk of the scientific talk of the conference. So I think it's somewhat appropriate that I'll try to discuss something which is perhaps a bit speculative, but certainly has been creating a lot of noises and excitement, and namely that's I need to try to do this. Oh yeah, that's machine learning in the context of MD simulations, okay? So before I get there, I'd like to discuss a topic that used to be more prevalent like 10 years ago. There were many talks where this topic was really discussed, namely the curse of dimensionality. Like, I remember that was really something that was popping out all over, and a bit less so these days. But what was the curse of dimensionality? Well, you can explain it in a fairly simple way, right? Which is take the Schrödinger equation, the equation that Ali Alavi explained to us, how to solve this morning, but just take it and ask yourself, why do I need to do anything fancy about this if I want to solve it? Why can't I just solve it numerically by viewing that as a partial differential equation, grading space, and then using finite difference or finite element and solving it? Well, the problem is the curse of dimension. Namely, that if you put the grid in space, well, the space is not the three-dimensional space, it's the three-dimensional space times n, where n is the number of particles that you have, so x lives in R3n, right? And so, naive estimates simply tell you that if you want to make a calculation and have a certain accuracy, say delta, small error, then typically the cost of representing the function will scale like delta to the minus 3n. So the cost explodes exponentially with dimension, okay? And that's the approximation error. And there's a corresponding problem or associated problem, which is that if you want to learn this function using already the language of machine learning, well, you also need the same scaling in terms of data point. You need to observe the function, if you wish, at a large number of data points. Also, same scaling, right? If you just want to be able to extract information that, about it. Think about the grid again, simply. Okay, so that's, that was the problem. And of course, if you had said to anyone, maybe 10 years ago, I'll just do that numerically with a standard method like finite element, people would have laughed because of this problem. They've said it's completely impossible, and it's quite well known. Okay, but then this happened, which is that we started to have machines that actually can play Go and, in fact, teach themselves Go and beat the best player within a day or two. And if you think for a minute about this, and you think about a game of Go as an input-output, which is that I give you a configuration of the board, and you need to give me what is the next configuration, so what you're going to do with it, right, which is what the machine is doing, in a way. Well, that's a pretty high-dimensional problem too, because so in the game of Go, if it's 19 by 19, right, it's 3 to the n square, the number of positions that you have on the board, because you can have a white, a black, or no stone. Not all of these positions are legal, so you need to take the percentage of that. And so if you estimate that, people have been looking at that for quite a while, you get this astronomically large number of positions that are available. Okay, and so that explains in a little bit so if you put that in the context of what I said here, it means that if you want to learn yourself Go just by observing configuration and then looking at the next one and saying, is it a good favorable one which would allow me to win or not, right? Well, clearly there is no way to have a data set that's complete. What the machine does is just observing an infinitesimal piece of what is happening, and yet it's working to the point that the machine is indeed beating the best player. So that's something which is very intriguing, because it kind of suggests that maybe when we were talking about curse of dimensionality, we missed something which is quite important. Okay, so I want to put that in the context of paraphrasing a paper by a fairly famous chemist, Wegner, which was called The Unreasonable Effectiveness of Mathematics in the Natural Science. In fact, that paper was given as a Courant lecture, which happened every year in the Courant Institute, in 59, right? And so I would like to paraphrase that and discuss about the unreasonable effectiveness of machine learning for a minute. And why is that? Well, because, it's clear that the machine learning has had this enormous, very profound impact on society. Not only there is Go, but there's this other topic, which is like, soon there will be self-driving cars. You can talk to your phone and expect an intelligent answer. I mean, all kind of things that were not deemed possible also 10 years ago. I mean, the landscape of what is being done in cognitive tasks by computer, image recognition, etc., has completely changed in a very, very rapid time. And so you can ask yourself why that's the case, right? And so you could ask, well, is there something which is, special in speech recognition or image recognition? Are they inherently low dimensional? Or, well, is it possible that in fact deep neural network could represent accurately high dimensional functions in ways that we didn't think was possible until not so long ago? Okay? And if that was the case, well, then maybe we could beat or at least alleviate this curse of dimensionality in scientific computing. And so that's what I want to discuss, a bit more in some detail now. So the way I'll do that is first by, I'm assuming many people in the audience are already users of machine learning, but I'm not assuming that all of them are. So I'm going to give you just a little, overview of what it is, what you need to do if you want to, train a network. And since I have an eye on scientific computing, I'll do that by taking the viewpoint that what I want to do at the end, what we would want to do, is to approximate a function. Okay, so what you imagine that you have a target function, f, that's defined on some domain which is fairly high dimensional, right? And you'd like to approximate it by a neural network. So this target function here, you should think about, well, the solution of the Schrödinger equation, if you wish, or a force field that you would like to parameterize, but the force field of the atom that you have, in the system, or the free energy of some collective variable, but maybe not 2 or 3, but like hundreds or thousands, right? So the way you do the representation in a neural network, in the most basic form, is essentially a superposition of neurons or units. Okay, I'm going to discuss here what happens if you have a 2-layer network, essentially, but all of this is generalizable. It's just for notation purpose. This is all generalizable to deep network, which is really the one that have, made the evolution. And so what is that? Is that the unit is this function phi that depends on 2 variables, the input, the x, which is the input of the function you want to represent, and then these parameters theta. And what you'd like to do is you'd like to fit these parameters in such a way that this Fn be a good approximation or representation of your target F. Fairly simple. And if you're not familiar with neural network, like the typical unit that one would take, the one that's very popular, would be what's called rectified linear unit. And so what is it? It's a weight, and then it's just a function which divides space into two, and then it's 0 on one side and it's linear on the other. Okay, you pick an hyperplane and you do that. And so here, for this example, what you would have to learn is this vector A, the scalar B, which is the position of this hyperplane, and then the C, which is the scaling, which is the slope that you would put on the linear part, right? And then what you would do is that you would get all of these guys and then superpose them as written over here. Okay. So how do you do that? What's the next step? Well, you introduce what in machine learning is called the loss function. And what's the loss function? Is simply something that measures the discrepancy between the target function you'd like to approximate and the neural approximation. And one, very standard and simple loss function would simply to take the square. You take the square of the difference between the target and the representation, and then you integrate it over space with respect to some distribution, the data distribution in the language of machine learning. So you can think about this integral as being the expectation over the data of the target and the representation. There are other objective function or loss function you could think of. For example, if you go back to the case of Schrödinger equation, well, if you minimize the objective function, which is here, right? That's the measure of discrepancy. If you minimize that, that gives you the ground state if you minimize with appropriate constraint. Okay, so that's what you want to do. Now, there's an additional problem, obviously, which is that in practice, you don't have infinite amount of data, which in the language that I'm using here means that you cannot do this integral exactly. So what do people do? They use a set of data, which is the training set. These are these XPs that are supposed to be drawn from this data distribution, whatever comes, right? And instead of using the exact loss, what you use is just an empirical average. So you estimate it over the data, okay? Which is what is written there. And then there's one more step, is the optimization step, which is that what you do is that you train the network, meaning you optimize the parameters, right, by what's called stochastic gradient descent. And so what is stochastic gradient descent? Is that you take the gradient not of the exact loss that you don't know, but you take the gradient of the empirical loss, the full empirical loss over batches of data. And then what you do is that you just do a step of steepest descent, so step of gradient, right, with a certain learning rate, this delta t here, and that gives you the update of the parameters. And then you repeat that with another batch, and you go on and on. Okay, so if you look at this, the first three lines here is just a summary of what I just said, the representation, what is the loss, and then what is the stochastic gradient. You see that you have immediately several puzzles, and we're going to discuss them in this talk. First of all is the one that I've already said. How, in this approximation, how does the error of the trained network scale with the size of the network? Right? If I put more units, if I make the network wider, if n here increases, what can I expect about the scaling of the error, or will it decrease? There's another problem, which is that you can also ask yourself, and that's very important, how does the error depends on the size of the data set? That means that if you train the network with a data set, and then you test it on a batch on data that you have not observed, how good will it do? And how does this error, this generalization error, will depend on the size of the batch that you use to train the network. Okay? And then finally, there is another important question, namely there is a question of dynamics or optimization, which is that they are the theoretical, what you can achieve in principle for the first two questions, approximation, generalization, but then there's another question which is actually, can you optimize this, right? And the reason why that's non-trivial, all of these questions actually, is that these representations are nonlinear approximation. The parameters that enter the neural network enters in a non-linear way in general, because the unit is a non-linear function, and if you have a deep network, it actually is convoluted on itself, so it's a very non-linear representation. Okay? So that means that the training is a non-convex optimization problem, right? And I want to, this is to be contrasted with what happens in standard numerical analysis. This was, very nicely explained in the talk by Gabor, which is that, more standardly, what you would do is that you would take a set of basis functions, these phi I that are fixed, and then you would just optimize weights. So if you look at what the loss would be in this context, right, what you would get is that it's quadratic in the weights, and so you can very easily minimize the objective function essentially in one go by solving a linear system, right? But this is no longer possible here because of the nonlinearity that you have there. In fact, in the case here, right, you can, in the standard case, the loss landscape is convex in the parameters, and so optimization is simple. But in the case of neural network, which are the ones that are successful, it's highly non-convex. In fact, it's a very rugged loss or energy landscape the parameters are evolving upon. And so there is absolutely no guarantee that if you do something as simple as gradient descent here, you will find a minimizer that's not a local minimizer and that is any good. Typically, you would expect that you will be like, we all know if you move on rugged landscape that you would be stuck at a local minimum that's fairly high in loss or energy, and so the operation will not be good. Okay, so that's a bit the puzzle, right? And so, the take-home message here, and that's what we're going to look a little bit, is that probably, this nonlinearity is both a curse and a blessing. The blessing is that it's precisely because they are nonlinear that probably, and we'll say in fact that's true, that these neural networks have better approximation properties. But the price to pay is that, well, they are much more difficult to analyze and optimize, because at the end of the day, standard numerical analysis is based on linear algebra. And here, you have thrown away that tool because it's a nonlinear system. And okay, that's that. Okay, so I will now, what I'm going to do is first discuss a little bit the problem of approximation error that we have, and then the one of optimization. And the reason why I want to do that is because I'll show you that, in fact, ideas that are very familiar to this community are very useful in the context of this neural network if you just revisit them in a certain way. And that's going to be my message, which means that, and I'll elaborate on that later, telling you that's really an opportunity for us, both to use the networks, but also to contribute into the development. Okay. So, first of all, there is something that we already know, right, that once you start looking at, that tells you that maybe, in fact, there is a chance that we can beat the curse of dimensionality. And that's the following observation, which is not new. This is something, these neural networks were introduced in the 40s, and some of the results that I'm going to discuss here are known till the 70s. It's just that they were not very popular because neural networks were not very useful or very used at that time, because there was no computer power to actually optimize them. But if you take, again, this representation here, right, you can look at something which is fairly standard. Imagine that I were to take the parameters in this representation randomly. So I just draw them from a distribution, and I'll call this distribution here mu, right? And I do that independently. Then there are two results that you know immediately. One is the law of large number that tells you that the function representation that you have at finite n will have a limit, and this limit here is just, you replace the empirical average over the parameter here by an actual expectation with respect to this distribution. First result. Second result is that, you know all the error at finite n scale, because that's the central limit theorem. The central limit theorem tells you that if you take the approximation at finite n, you subtract its limit, you multiply by square root of n, that should converge in law, in appropriate, under the right assumption, towards some Gaussian fields. So in short, we know that this Fn, if n is sufficiently large, so if you take a large number of parameters in your neural network, right, is a function f, and you know what it is this guy here. Well, you know it is in principle, right, plus an error which is of that type. Okay, this is nothing but the standard scaling of the error that you have in Monte Carlo that I'm giving you here. Of course, I mean this is just all in vacuum because I have not connected that to the actual target function that I would like to represent. But there are also results in that direction that also exist for a long time, and that are generally referred to as universal approximation theorem. And they are, they were developed by Baron, Shibenko, Park, etc. And what they say essentially is the following. They say that if the unit if essentially is nonlinear, that you can, meaning this is this discriminatory property here. If you give yourself any target function, then you can approach it arbitrarily close with a neural network if you take sufficiently many units. Okay, so if you want to, write that in math, it's essentially saying that the L2 norm of the difference can be made arbitrarily small with a function that is in the class that you can represent by neural network. Okay, that's a very interesting result to have. It's nothing but essentially saying, if you wish, that they are complete in the same way as if you were, to use, I don't know, Fourier basis. It's a complete basis. So this is not a basis really, but it's saying that neural network have approximation power in principle. You can represent pretty much any function you want with them. Well, that's a good thing to have. And you also know that not only they are representable in this way, but you can do that in practice, because how would you do that? Well, if you knew what this measure mu star here is, you could always draw the parameter independently from it, and that would give you the representation with the law of large number guarantee that it converges, and the CLT guarantee that there's an error that scale like n to the 1/2. Okay, so the universal approximation theorem, what it tells you is that it gives you the theoretical approximation power of the neural network. One thing. Okay, it also gives you an error, and in fact you can push that a little bit harder, and it says that you can show, that the error on the loss, this is just the square of what I was saying before, scale like a constant divided by n, where n is the number of units in your network. And then you can do, a bit more work, and you can also show, using similar tool, that the generalization error, meaning if you train the network on a finite set, data set, and then you test it on something else, will scale like 1 over square root of p, where p is the size of the data set, is the size of the batch. Okay? And the constant, so this all framework this all result give you a framework, because it also tells you that the constant that are here are related to the norm of the target in some space, which is the space that you can represent with this function. I'll get back to this point because that's an important one later on in the talk. So in principle, the universal approximation theorem gives you a way to not only quantify the accuracy of the networks, but since you have access to the constant, in principle it also tells you how you can optimize the architecture of the network. The thing, in fact, in this result is what people have been using, for example, in convolutional neural net. They do it in a more practical way, but to actually show that you can diminish these constants. I'll get to that in a minute, okay? And this can be generalized to deep network. So I'll get back to this result in a minute, but before that I want to discuss something else, which is that the universal approximation theorem doesn't tell you how to optimize the parameters. It doesn't tell you what is this measure that is here, and in particular, it doesn't tell you that if you don't do what I suggest here, it's completely academic and impractical, of course, which is to draw the parameters from the measure, which is the optimal one, but instead you try to train the network by just moving the parameter by a stochastic gradient, that this is one and the same thing, that at the end you will end up in the same place. Okay, so I will discuss this a little bit because you will see, this is maybe the only contribution in the talk which is really ours or mine, which is to show that by borrowing tool from statistical physics and statistical mechanics, you can actually answer this question in a way which is very satisfactory. So let's get to that, and then I'll go back, to the MD step. So let me discuss what is, training by looking at gradient descent on the exact loss. You can do the same analysis on the empirical loss, doesn't really matter. It's easier for notation just to think about the exact loss. So what you have here is that you need to think about this in the following way, and it will become fairly clear quickly for this audience, which is that if you look at the loss here, right? If you think about this as an objective function in the parameters, well, you can expand the square, and then you can essentially write it like that. So it's a complicated, it's an energy, which is fairly complicated in the parameters, which has this form where there is a term that involves a single sum, and that's the one that see the target function through this expectation or this integral. And then there is an interaction term. We'll use this thing in a minute. That is given by this. Okay. And then gradient descent is, if you think about this from, not as is done discretely in time, but if you think about it continuously in time, is simply you take the gradient of this loss, right, and you evolve every parameter, so every theta I in the stack, just by using this steepest descent, like, the one where you go down in energy, okay? And I'll generalize that later to stochastic gradient descent. Now, there is something that you can do here which is quite simple and quite natural in this community, which is that you realize that, this landscape here is fairly complicated. I have said that several times already, and probably non-convex. But at the end, you don't care, if you look about what's going on here, you don't care what the particles are doing individually. What you care about is what the function representation they produce as they evolve, okay? And so you can realize that if you think about, the parameters as time-dependent, this theta I of t here, right? You can think about, this is just a rewriting of the line that is there, you can think about the representation of the function as an integral with respect to the empirical distribution of the particles. You just put a little Dirac at every particles, and then you sum over them. Okay? Why is that useful? Well, that's useful because once you start doing this, you can actually write down an equation for this empirical distribution. This is essentially chain rule, right? And what you obtain is you obtain a variant of the Liouville equation, except that's a nonlinear Liouville equation. And why is it a nonlinear Liouville equation? Well, because of the quadratic interaction that's there. So the equation is written here. Okay? Once you have realized this, then you can start to analyze, and this is all for analysis. It's not, at the end we won't change anything about what is done in practice, but you can start to analyze what this dynamics is doing, okay? And in particular, there is something that you can do, which is quite natural, which is to take the hydrodynamic limit, which is what happens if n goes large, okay? And let me give you a little, you all know what is hydrodynamic limit, but I'm going to give you, a little movie just that illustrates what it does, because it's the only movie I have. And so it's an example. It's a bit misleading because it has nothing to do with machine learning. It's in fact a standard particle system, like we like, to have them. So what is shown here is a blob of particles. They are the white dots that you see here, and what they do is that they evolve on a landscape, which is the double well that you see under them. But they also interact, and they interact by repulsion. Okay, so there's a Coulomb repulsion in this case. So what happened is that if there was not this repulsion, they would all move independently from one another, and they would all fall into, if from this configuration here, they will all collapse into the local minimum on that side of the double well. But since they push each other, that configuration is not energetically favorable on the actual landscape they evolve upon, which is the landscape where they all interact, okay? Because there's a trade-off. They want to be away from one another. So how do they manage to be away from one? Well, they want to be away to one another, but staying low in energy, okay? And so what I'm going to show you in the movie is simply the steepest descent dynamics of these interacting particles. So there's no noise here. There is not. They just go down on an energy. You just need to remember that the energy they go down on is not the one that you see here. Is the one that include also the interaction potential. And if you do that, what you see is this. And I think once you have seen the movie, you understand why it's called hydrodynamic limit immediately. Most of you already knew that, right? And you realize that. And that's very natural for people like us that do statistical mechanics, but not so much for machine learner or people that do standard numerical analysis. You realize that what these particles do individually, I do not care. What I only care about is what is the distribution, the underlying distribution, which is the one that I was talking about on the previous slide, right? I don't care if I tag one of these particles, what it will, I might care, but in general I don't, which is, what an individually tagged particle will do. What I'd like to know is what they do globally, okay? So if you understand that, well, you can take the hydrodynamic limit, or it's also called the mean field of this equation, of this nonlinear Liouville equation, and you can write down an equation for them, and what you realize is that this equation is actually very simple, because at the level of the measure, which is the one, if you don't look at the particle, but at the level of the measure, you see that what this equation is simply a gradient descent in some specific metric, so if you wish with a given mobility, on the loss itself. The loss that you see no longer from the viewpoint of the parameter, but from the viewpoint of their distribution. And the nice thing about this, which explains in a way why the networks are trainable, is that at this level, if you look at the energy, it has become quadratic in this measure. So it's nonlinear in the parameter, but it's quadratic in their distribution. So if you think about what's happening at the level of distribution, it just evolved on a quadratic landscape. In fact, the one that is written there. Okay? And so what does that mean? That means that all the ruggedness of the landscape that you see at particle level, and that is there to stay, is somehow not visible if you coarse grain the description and you look at their distribution. Okay? And these are results that we published in NIPS last year, and there were similar results at the same time by other group, in particular the group of Montanari and Speliopoulos. What they allow you to show is the following thing, which is, and the reason why I'm spending a little bit of time describing this is really because I think it should be appealing. It's an explanation that should be appealing to this community. What it allows you to show is the following thing, which I've stated as a proposition here. It's essentially that if you suppose that I look at this function fnt, which is the neural network representation in which I take the theta I, which are my parameters, I draw them randomly initially from some distribution, and then I evolve them by stochastic gradient or by gradient descent on the loss. Then what you can show is that this function has a limit as n goes to infinity. That's the same as the law of large number that we wrote before, except that now the one that we had before was a static result. This is a dynamic result because it comes with another statement, namely that this function, this limit function, converge towards the target function that you want to represent. Okay? And if you work a little bit harder, you can actually prove that the two limits here commute, meaning that you can take t to infinity at finite and then n to infinity or the other way around. Right? What does that tell you? It tells you that these universal approximation theorems that they've been around for quite a long time but were academic because they were static, you don't know how to get there. In fact, they have a dynamical aspect to them, which is just to say, well, if you do gradient descent, in fact, it achieves the universal approximation theorem. Okay? Now, if you're a statistician here, there is something that is a little bit unsettling in this, which is that, namely, that the model is not identifiable. If you think about thetas as parameter, in fact, it's the same if you're a numerical analyst, in a way, which is that each time you do this, think about the particles that were on my previous movie, you draw the particles or the parameters randomly, you evolve them, you get a different solution. All the solutions have the same approximation quality in the limit, but they are all different. Okay? So that's a very different way to think about numerical analysis in a way, because typically in numerical analysis, you'd like to know what is the solution. I mean, when you optimize, you do finite element, the coefficient have a value. They are not random numbers that can vary from time to time. Here, that's what it is. And that's very well known, of course. If you train a neural network twice, and you look at it, you have different neural networks. They do as well, but in the detail they are different. And these results are saying, well, it's because you don't look at them in the detail. That's what matters, and you can show that that's the case. Okay. Now there's another aspect which is and I'm going to go on that, is that these results also hold if you look at the empirical loss. Okay. That's fairly, and they give you an approximation error that scale, that's the CLT. So just in the same way, there's a dynamic counterpart of my central limit term that also applies, that tells you that the error scale like 1 over square root of n, the representation error that you do. And then if you work a little bit harder, you can also show, and I'm not going to go through these details, but you can also show that if you rigorize the loss, that's a little point that, I don't want to go into in too much detail here, right? You can also show that you can find what is the generalization error. And what you obtain is essentially something which is like this. It tells you that if you train by stochastic gradient descent your neural network, what you're going to get at the end is that the error that you do, this is the loss that you will do. So the loss that you have between the trained network with a finite amount of data set and the target evaluated on the full data set will be bounded by constants. One is divided by n, the other one is divided by square root of p, and then there's an additional term that comes here that can be made arbitrarily small. That is the regularization that you go from that you need to put in the loss. I might discuss that in more detail in a minute, but it's not super important. Again, these results were known, but in a static context, and this is just revisiting them from a dynamical viewpoint. Okay? What is important here is, and that I want to emphasize very strongly, because this is really the key for application, right? Is first that these are the reason. So you notice that if you look at the error here, there is no in the scaling in n and in p, the input dimension is not there. It's not n to the minus 1 over d, which is what you would expect from the curse of dimensionality. That you would expect that if you put a grid, right, in d dimension, how many grid points do you need? N to the minus 1 over d to achieve a certain error. This is not what you see here. It's n to the minus 1, which is truly remarkable, right? However, there's two catch with this. One is not really a catch. It's just that it's a change of perspective, which is that standard numerical analysis, the reason why you get these fairly bad bounds is because they are typically interested in the worst case scenario. This is a probabilistic bound, right? There are expectations here. I mean, because at the end I'm using framework of particle system and probability. This is just telling, on average, this is what is happening. It could go badly, and if you ask, how badly could it go? Well, it could go very badly, but that's very rare. Okay? If you want to, again, worst case scenario is bad, but it's not happening. You can, in fact, change this probabilistic bound here by, these bounds in moment by probabilistic bound using concentration inequality. I'm not going to discuss that. More importantly, perhaps for application, because this is really, one of the strongest messages that I would like to pass here, is that even though the scaling in n and p do not depend on dimension, the constant do in general. Okay? What is nice is that you have a priori tools to analyze what these constants are now, because they are given explicitly by a certain expression. And what is the advantage of that, right, is that in principle, this tells you that you can, it gives you a route by which, in principle, you can optimize the network architecture, meaning which unit you use and how do you organize them, right? Because, and that's really the point that I want, that needs to be emphasized very strongly, is that these results, even though you have beaten the curse of dimensionality in terms of the scaling in n and p, these results are only practical if the constant that you have there are reasonably small. If the constant themselves are exponential in dimension, you would still need an enormous amount of data. And that will be, the rule more than the exception, especially if you take a neural network off shelf that has been designed for another problem and you try to apply it to your problem. That typically, there will be no miracle. Okay. So I'll emphasize this conclusion again in a minute. I'm almost at the end of my talk already. The only thing that I wanted to do now is, this was a bit of an overview of what we have done. I just want to give you an overview, very short, of a few applications that have been done with this that are reasonably successful. I don't think that there's a call for a lot of analysis, but the application works. So the first one, well, I can come back to the problem I started from. Well, the Schrödinger equation has been analyzed in specific case using neural network. That's the work of Matthias Treuer and Giuseppe, oops, wrong button. Matthias Treuer and who was here yesterday, I don't know if he's still there, and then Giuseppe Carlo, where what they do is that they use, in a nutshell, read the paper, they use a neural network representation of the wave function, and as a loss, well, they use this loss. Okay, and they optimize and they show that work. Okay. Now there's another context where neural network, and we have heard about that already in the talk, where they are they are becoming increasingly popular, and probably is one of the the most natural application of them, right? And that is force field estimation. Okay, and the idea here is that instead of trying to adjust the force field very painstakingly by doing all kind of trick that we have done, I say chemists, have done for a long time, you just throw at them a neural network, use the data that you have and train the network, okay? As usual, I mean, Ron, who is always a bit of a precursor on anything, had done that quite a long time ago. This is a paper, and so did Michele Parinello. But since then, many papers, have appeared, and we have seen talks here. There was a talk of Gabo Oxani, that also has worked on that. There was just before there was the talk of Michele Ceriotti, which also has worked on this. Wen and has worked with Roberto Carr, and is doing that. And the idea is pretty much always the same as the one I said. Is you use a Bayesian framework with random kernel features or random feature kernel, or you use neural network that you train on data, or you get the data, well, either by experiment or by DFT calculation of some type, some quantum calculation, okay? And you train your network. And the advantage of these methods is that they are very versatile. What this paper, however, show, and that's like, something that is the same point, of course, with the one I'm saying, is that the architecture is really very important here. Like, I mean, you cannot use the networks that were used, for example, to process image in this context, or at least you need to adapt them, because you need to preserve the symmetries, okay, at least. That's one step towards this analysis on how the constant depend on the architecture of the network. One more application is free energy calculation. Free energy calculation is, well, the idea is the same. I mean, I'm just showing here 3 papers, is that you want to do a free energy calculation. Well, the free energy in some collective variable can be represented by a neural network or radial basis function. We did that with Luca quite a while ago. And then you just get the data by doing umbrella sampling or blue moon sampling to get estimates of the mean force at certain point. And then as loss, you look at the discrepancy between the mean force that you observe at this point and the one that you can calculate explicitly on your neural network representation or your radial basis function representation, and then you just optimize, okay? And these methods are also fairly versatile in the sense that they allow you to do free energy calculation without having to think about where you need to put your umbrellas, what's the representative, what's the binning that you need to do and all that, and potentially scalable to higher dimension than the one is typically used to for free energy calculation, meaning 1 or 2. Here you can go much higher. And then, more recently, that's a bit of something which is a bit different from what I've discussed, but I can also be put in a similar framework, which is that you can do that for Boltzmann sampling. And this is something that has been, pushed forward in particular by Frank Noe and his group. The idea here is actually quite simple. What you would like to do is to use this formalism of normalizing flow that we introduced with Esteban Tabac a while back and was popularized by these guys in the context of machine learning. And what is that? Is that it's essentially, imagine that you have a set of data points from a distribution. You use a Bayesian approach to try to construct a map that will map these data points onto a Gaussian. And then once you have done that, you can interpolate very easily on the Gaussian and give you new data point. Okay? And so this is the way they do it here, is in some form of inline or online learning, where you build the map, and as you build the map, you get more data more efficiently through the map. And that's a form of important sampling. So my time is almost up, so I'm just going to flash by you a few conclusions, and then which is that, so there are a set of theoretical results that starts to indicate that the overwhelming empirical evidence that we have that neural networks do work in high dimension to represent function, in fact, that you can justify that and put that on a firm theoretical basis, both in terms of approximation and trainability. Okay? This obviously offers very exciting possibilities for scientific computing, and this community is already exploring them, and that's a very good thing. However, as I've already said many times, it's not going to work unless you optimize your network the right way, which is the point that is being made here. So you need you need to work hard, otherwise it goes the same way people doing image recognition have done. Okay. And also there is this counterpart, which in fact this point was made by Christoph Schutter yesterday, which is that machine learning is useful for statistical physics or computational statistical physics, but the other way around is also true. Computational physics has a lot to offer, and I hope I demonstrate that a little bit with this result into the understanding that we have of machine learning, right? And then finally, just because it's the last talk, and of course, this representation of function in high dimension raise interesting question in terms of interpretability of the results, and I will simply take question by leaving you with a little poem or text by Lewis Carroll, who understood everything before everybody else, that tells you that having very good maps is not necessarily a good thing. So I'll let you read that, and I thank you, and we'll take questions.
Thank you very much for a wonderful talk. There is some time for questions, and so who would like to start? Oh, I see. Sorry, is me? Wait, yes, there. Yeah. Sorry, you need the microphone, but then yeah.
Eric,
Mark.
thanks for that really, really nice talk.
Yeah.
So much of what you described obviously is for function fitting and what I guess is generally the regression problem. But so I'm wondering, since machine learning is also these neural networks are also used for classification problems and n-channel classification, how much of this actually can generalize to that problem, so that, for example, there may be a guarantee that I can get 100% classification accuracy if I design the right network with all of the heterogeneity that you might have in, convolution networks or the things that people actually use with these very, very deep architectures. I mean, is there a way to kind of go in to generalize all this, or?
You mean to analyze that, or to use these tools in the context
do the classification problem? Because there are different loss functions that are used and things like that.
Right. So these are the. I went fairly quickly. They were referenced. These are problems that we are now looking at with a colleague of mine at Coron in the data science department there, Joan Bruna, who has contributed a lot into this convolutional neural network for in the context of image processing. So these networks have, and for classification, they have a specific structure that is amenable to the same type of analysis as this. They are deep network, but they have some structure that I'm not going to go into detail, but we think we can analyze them in the same way. And so potentially it offers a possibility to explain why they have been, or have an element of explanation as to why they are so successful.
Yeah.
Yes. Now, maybe just, it was not your question, but one little comment. I have not discussed that, but you could, just related to this, in fact, you could also, and we had also talked about that in this conference, you could also think about using machine learning to do automatic coarse graining, maybe not classification, but finding collective variables.
Yeah.
Right.
Okay. Alessandro.
Does this,
Wait, I'll give you my phone, as long as you give it back.
does this mathematical analysis tell you something about the reason why neural network do not overfit even when they are strongly overparameterized? There was a very nice talk yesterday in another room addressing the similar question. So this thing is, in my opinion, a really central problem, especially in practical application, and it's even more a problem in the presence of misclassified data in your learning set. And I was actually wondering if if by using this technique you can learn something about this problem, because
You
finally
do, because I mean, if you know the overfitting problem, right? You address it if you address the problem of generalization. It's one and I mean, it's one and the same thing, right? And so you know the result here, which built on previous results, you know, indicates that you can quantify what is the generalization error. And get these bounds where the constant typically will not be very good. That's the one that is the more, you know, the more worrisome, right? So that explains why, I mean,
Okay.
I don't know if that's an explanation. That explains why they don't explain why they don't overfit.
A very brief question and an extremely brief answer. Yes, please.
Okay. Is this a danger in the machine learning to replace the curse of dimensionality with the curse of non-linearity? So instead of going straight to the attractor point, you can go like strange attractor or like oscillation, something like that. That is usual process in a neural network, right?
So, well, I mean, the point of the talk was, I mean, what I tried to explain is that indeed they are nonlinear if you look at them from the viewpoint of these parameters. But if you take, you know, an approach is fairly natural for anyone who does statistical physics, namely that you look at the distribution, you eliminate this nonlinearity, and that's the way to do the analysis.
Okay. I think we have to stop the discussion here. I should like to thank Eric once again for a wonderful talk. And so before I give the microphone back to Ignacio to conclude this meeting, I think that I want to say a few words about the meeting itself. I think it has been an absolutely wonderful meeting, organized extremely well, and we all know that both Ignacio and Sarah did an enormous amount of work to get this together, and then they have this whole team of the CECAM crew who did made this whole thing work essentially in such a way that you didn't even know it was being organized. It was so smooth, and I think we should all give them a great round of applause for what they've done. Ignacio, the final words.
Thank you, excellent.
So, for good or for bad, everything comes to an end, and that's also the case for this conference. I think these have been 3 very intense days of scientific exchange, and I think that we hope we have accomplished what was one of the goals when we start thinking how to celebrate CECAM and how to organize a special event that would combine both having excellent science, bringing really to all of us what are the challenges in all areas that are relevant for our communities, and at the same time to manage to get a space for meet each other, for recognize us as members of CECAM and value what CECAM has represented for our community and how we wanted to keep it ongoing in the future.
Yes, so everything must come to an end. Yes, we are practicing this. Everything must come to an end, but in any end, there is also a beginning. And so CECAM keeps thinking about what is going to happen in the future and how we can best survive crises and improve the services that we offer to the community. Now, many of you are aware, because you have suffered the consequences with us of this crisis, that the CECAM website had a bit of a problem last spring, and that we have been operating on emergency measures ever since. So we have been working to solve this problem, and we thought that this might be a good opportunity for us to show you where we are and give you an idea of what the new CECAM website will look like in the very near future.
So yeah, so this is a bit of a spoiler. As I said, I think CECAM has learned to move on from crisis, and after the evaluation, we thought it was better to provide a new server. After all, this is most of the time the face of CECAM for all of us, and it's important that it provides a good service. So we expect to deliver, to have the new portal in place by the end of November. But just to give you an idea of how it will look like, this is the static part, where now in principle should be easier to scroll down so that you can go through the news. The events are better structured, and also everything that has to do with the information about CECAM and any other activities. And here in the menu, actually, we also have a structure and organize a bit better the information about, for example, the governance, so you can see better who are the members. Scrolling through the notes will be more interactive. There will be whatever you have heard about the history that we have been collecting will be systematized through here. Also, the program will be hopefully more flexible and easy to access. I'm not clicking too many of these buttons because they are, in many cases, still work ongoing, but the whole structure of the program is better integrated. And also, when it comes to how you can submit proposals and get the relevant information also for application, I think all this will come much more dynamical. And again, we will also build on news and careers and other activities. So keep an eye. We will announce this at the end of November, but I hope that for next year we can then close the transient one that Sarah was saying, and we will operate on this much better server portal that will provide a better service for you. And to finish, I think that Dan already mentioned the acknowledgements. I should start by saying that this is obviously the first people to thank is you being here, participating, delivering the lectures, bringing the posters, asking questions, making this really a fruitful, dynamic event. As you can imagine, this has been a collective effort. Many people are behind making this a success. I think it's also a moment to recognize, as I said, scientific excellence was really an utmost important from the very beginning. And the program was built together with the scientific committee. Most of the members are here. Unfortunately, Claudia Draxel couldn't make it. I think we should be grateful for their commitment and for the very honest and transparent discussions we had to really think in the best possible program for this event. I hope you appreciate that. Also, part of the scientific committee, Alessandro Laio and Rodolfo Bilumer as the president and vice president were involved, and they have also been, through our regular meetings, driving us in shaping it properly. So I think they also should deserve a recognition. When it comes to the place, again, we thought that SwissTech, having this space for us, was also a good way to keep us together in a comfortable environment. So we should thank the people from the SwissTech Convention Center to make this possible, particularly Tamara Richard, Julian Mayor, and Nicolas Menino. I hope you enjoyed the coffee breaks and the lunch. That was work we did with Eldora, so we should thank also Kathleen Dennis and the team. But I think that, as already Dan was hinting, we should really, this wouldn't be possible without the local team. You know that CECAM, we are a small team. This has been an exceptional event. So I would like to call to the stage all the people that have been involved in making this possible that you have not seen. So Kieran, Eduardo, the external students that we have, the research team. I would invite you to come. Guy and Bogdan should stay there, but yeah, please. So no,
so they
have vanished. Okay. Okay. So you see that sometimes, yeah, yeah. Okay. The students left.
Where are our external students, Kieran?
I have freed them of their duty.
Okay, so they run away as soon as they come.
So the students run away, but okay. So I think they are. I mean, definitely you have seen them with the external students with the white T-shirts and the young members of our research team have played an important role in handling things around and ensuring that providing continuity. So, so research, but they are not here. Yes. So. Huh? Yes. No. But yeah.
Okay.
Yeah,
wait. Give us time. Give us time. So we've had some external students, but we also have the research students and postdocs at CECAM. Now, working at CECAM is a great adventure, and they have learned that the hard way. So thank you very much, Shen. Thank you, Eduardo. Thank you, Helena. Thank you, Cecilia. I'm sorry. I'm really, really super tired. And Damian is somewhere, and the guy standing behind the camera there, he's Alessandro and has been helping us as well. So please, a round of applause for them.
So also, you have not seen much of, again, we are missing Natalie, who probably already left, or is hiding there, and Katarina, who have been upstairs, always ready for any question and have provided support from many of these hidden small things that you don't see, but they are really instrumental to ensure that everything flows. So I think they also deserve an applause. Also for Natalie.
And then, of course, Kieran, our event coordinator here. Now, Kieran really had to jump on a train that was running very, very fast because she joined the team about 2 months ago. Yes, 2 months ago. We were talking about crisis this year. Michele Ceriotti at some point suggested a voodoo rite to simplify our life at CECAM because we've had, unfortunately, problems related with the permanent event coordinator who's had health problems. And so she had to leave us on sick leave around May or June, which is not exactly when you want to see your event coordinator leaving if you're organizing a conference like this one in September. Kieran came on board, and she was fantastic in helping us keep things on schedule and running it. She has also been the invisible force coordinating all the students and the staff's work here at SwissTech during this conference. So thank you, Kieran, very, very much.
And as I say, they cannot be in the stage, but obviously Bogdan and Guy, also with the support of Gianni Notaro, have played a very important role in all the audio and streaming, ensuring that everything related to how things go here, it's okay with all the previous work to prepare everything. And also, Guy, I think Guy and Bogdan, you can stand, no? While this moment, you don't need to look behind. And Guy has really been acting as a coordinator for the whole event, and you will have also seen the effort we have made to have a more systematic and clear image of CECAM, and also Guy has been the driving force behind. So I think without all this magnificent team, this wouldn't have been possible. So thank you very much to all of you, and I'm sure, some of them you will find meet in CECAM, and they will keep on doing his extremely good work. So thank you very much.
Thank you.
Okay, so this is the end. I would be tempted to say, see you in 50 years in the 100th celebration of CECAM. I'm sure it will be an outstanding celebration when it comes, but I hope we will keep on meeting through the CECAM events, and that we will keep on evolving together, and that CECAM will keep playing a useful role to all of us. I cannot finish without one technical point. We should leave the building because they have to prepare now the building for the afternoon. So, but CECAM facilities on our headquarters is open to host you if you need to be around for the rest of the day. So have a safe trip backwards, and thank you again for making this a successful conference. Yes, those who have posters still posted, please take them away before they disappear.